Good. I've already given 27 parts. Actually, I know. Of course, so that one actually 1 hour. Yeah. Okay. So that's great. Okay, so. So, yeah, absolutely. So, 15. Yesterday, Then I get something first. Oh, you have right. Like, no, yeah, like I'm not to see there, but I think it's kind of goes out. I went and I got to the first.
Okay, let's get started. Any questions before we actually start today's lecture? Everybody actually get the power solution? Encounter any difficulties? So I was, some of you actually emailed me recently, the past couple of days, right? I also might reply to everybody. If I haven't, please follow up. Okay, and one thing that I don't give a very certain answer is that I received this email saying that this actually my I took CHEM1312 long time ago, so I feel like I lost a lot of my memory in the past. Right. So this week, if you can see on the syllabus, this week there's actually one homework for you, right? Which is due on August 31st. Okay, so this is actually your first homework and first quiz. Okay, so this actually can't give you the time, so you can go back to this specific section. Okay, so you guys have the textbook. You know what section that is. Okay, go back and reload things. Then each actually cover most of the things that you need for CHEM1312. Okay, do it. Don't fall behind. Okay, so the things that you don't really succeed and pass this class. Number one rule, understand everything in the lecture. Okay, don't fall behind. Do your homework at the right timing. It's very important. Okay, the other suggestions I will give you is that form a team. It's very important. Okay, don't make a team too big. 2 to 3 people typically is the best. Okay, why? Why do we do this? Because we all see that from the previous lecture, the things that matter the most is your exams, right? 80% of your score coming from the exams. So the way the exam was formulated is that the chemistry have a super big data bank. Okay, so let me have 10,000, 20,000 questions within the data bank. And when you go to CASA, they randomly pull the question for you. Okay, so every time you do your homework, every time you do your quiz, everybody got slightly different questions. Okay, and those are part of the data bank. That means if you have 2 people work together, first you can check on each other to understand the material. Second, you maximize the chance to see the number of different questions that you're going to encounter when you do your midterms. Okay, so if you haven't done so, try to actually find a friend, one or two, don't get it too big, because once things get too big, there will always be someone who is actually drop the ball. Okay, so just find one or two friends you, and then work together so you can understand the things better. Okay, and there will be actually a homework for this week. If you don't know, all these things were supposed to be on Teams. Okay, so make sure you do every single homework in time. So it's very important that you can use the homework to test how much you understand or how much you don't understand. Okay, if you don't understand, come to me. Okay, I will make you understand. If the office hours doesn't work for you, email me. We can make an appointment. Okay, I can be your tutor. Okay, but you need to actually take the initiative. You are the one who can make this happen to you. Okay, so don't screw up. All right, so this is actually the first thing I want to mention. Any questions so far? If not, then what we're going to do today is actually first, I want to make sure you've got your PowerPoint solution. Okay, so the section ID that we're going to use for the rest of the semester is CHEM1312. I missed a few letters here. Section ID is CHEM12, 18785. That is actually the exactly section number of our course. Okay, so we're going to use these numbers throughout the semester, and we're going to do the test today. Make sure you know how to check it out to the point solution. Then we can start taking advantage of that specific app. All right, so 101312 18785. All right. But before we go into there, I want to actually give you a quick rundown about what's going to happen today. Okay, so on the screen, you see actually left and right hand side, right? So the things on the left are the things we have learned in our previous lecture. Okay, so in the previous lecture, we started to talk about concentration, okay, different concentration terms. Okay, and we know the solution is composed of solvent and solute. Okay, so mass of solution is the combined mass of solvent and solute. Okay, and when we talk about the concentration terms, we need to actually know the mass of your solute, the formula weight of your solute, so you can calculate the mole of your solute. Okay, so I'm talking about this. Right, and these things, why do I draw? Why do this rundown? The things I draw is the things you have to memorize. Okay, so this is actually kind of the condensed version of the things we went through in the previous lecture. Okay, so these are the equations that you actually memorize. Okay, so once you know how to calculate the mole of your solute, then we start to actually talk about different concentration terms, starting from the molarity, capital N, which was defined as the mole of your solute divided by the volume of your solution in liters. Right? This is actually the second line here. Okay, and then something that's actually relevant to the molarity is actually the normality, which is simply the product of your molarity multiply the number of equivalent. Okay. And after that, then we start to talk about the other three concentration terms, mass percent, mole fraction, and the molality. Okay, mass percent, mole fraction, and molality. Okay, it was defined as the equation highlight over layer. Okay. This is actually the one where the denominator is using the property of your solvent only, right? It's actually the mass of your solvent, not mass of your solution in kilogram. Okay, So we went through one example in the previous lecture. We're going to go through a little bit more today. Okay. And at the end of the previous lecture, after the lecture, a few students come to me and ask me, when we are going to use the information of density, right? Because in our previous example, even though the information of density was provided, it was not used, right? And then the answer to that is, if the concentration conversion doesn't involve the molarity, then you will never use the density information. Okay, we'll give you one more example today. Okay, but let's actually have a quick rundown about the things we've been going through in the previous lecture. All right, and what we are going to do today is to finish all the contents for chapter 10. So we are going to finish everything for chapter 10 today. Okay, which your homework will be due next week. Okay, so the reason I want to get this done early is because you can start your homework early. Okay, don't fall behind because it's really difficult to come back because it's just going to get easier and easier, having more and more fun during the semester. Football season is coming, right? There's just too many activities you need to do. So if you're just, go off the track, it's very difficult to come back. Okay. So what we're going to talk about today is actually only two main topics. First topic, we want to actually, so by now we should actually learn or have some idea about what concentration is. So the next question the test will try to teach you is actually what are the factors that can affect the solubility. The solubility means actually the concentration of your solute inside given solvent, right? If you increase temperature, how will actually change the amount of solute that can stay inside your solvent. Okay, so if you change your pressure, how will actually change the concentration. Okay, so those are the first things that we want to actually learn. The second thing is called collective properties. Okay, so collective properties is also one of the big sections we are going to encounter a lot of calculation problems. Okay, but the idea is actually very simple. Those properties, okay, we're going to talk about collective properties actually mainly four things. Okay, and those are the four keywords that you will need to actually memorize by the end of today's lecture. So these are the four properties that only depending on the amount of solute inside the solution, but doesn't care about what kind of solute that you have. Okay, so the four property is first, BP stands for vapor pressure. Okay, FP, freezing point. BP, boiling point. Okay, and the very last one, OP, osmotic pressure. Okay, so these are the four properties. You're only depending on how many solute particles you have inside your solution. Okay, and the conclusion we're going to end up with is that if you throw in more solute particles, okay, your vapor pressure will drop. Your freezing point will drop. Your boiling point and osmotic pressure will go up. Okay, so those are the take-home messages that I wish every student can get when we finish today's lecture. All right, so that is a quick rundown of today's lecture, lectures. Any questions so far? Okay, if not, then let's test our point solution. Okay. Okay, so let's start from the simple one. The first one. Okay, so use your phone to actually give me some instant response. Okay, get yourself familiar with the setup because these are things we are going to use for the rest of the semester. Okay, so in the beginning of the class, I will actually give you a few questions. Okay, and those questions will be designed to test yourself, like how much you understand the material we went through in the previous lecture. Okay, so this is actually how I can actually confirm that majority of us is still on the right track. It's also a good way to let you know whether you actually still, follow the lead properly. Okay, so we have around 81 people is using this. 82. Okay, so trying to actually reuse this. Okay, so chemistry is actually most notorious subjects, right? So I always get this every time. Yeah, so why? Because it's hard. Every single subject is difficult, right? Or why chemistry is actually most notorious? Because most people do poorly in chemistry, right? But why? Yes?
There's a lot to know.
Hmm?
There's a lot you have to know.
Yeah. So the things I think why chemistry is actually difficult is because it combines many concept-wise it's actually not difficult at all. Okay, but I feel like the chemistry teaching has some problem. Okay, meaning that we deny to teach you in a way that it makes sense to you. Right, so people feel chemistry is actually hard. Okay, so from my previous teaching experience, okay, many people actually come to me at the end of the semester says, I can never imagine that chemistry not become one of my favorite subjects. Okay, simply because that I make the material make sense to the student. Okay, so that's actually my goal. Hope that the way I teach will start to make you feel like chemistry is actually somewhat makes sense. All right, so I will provide more like when we learn these things, how it's actually related to the things you observe in the daily life. Okay, that will be actually my goal. Okay, but so far I feel like it's cool. At least more than 100 people that we know how to actually use the point solution. Okay, so I want to go to next. All right, let's try another one. Okay, this is actually testing like how much you know now, because we just went through the things of previous lecture, right? Yes. So if you have problem to get the point solution, okay, I will post who to contact, so you will be able to get the app. Okay, I'll post that on Teams after the lecture. Is that okay? Yeah. Okay, so this one is multiple choice though. It's not just one. It's not just a single answer. Okay, which of the following are not a concentration term? Okay, good. So we have about more than 100 student answer, right? So yes, the answer is actually density and mole. They are not the concentration terms, right? So we talk about 5 different concentration terms in CHEM1312. Okay, the first two is actually molarity, capital M, and molality, capital N. Okay, and the other three is actually mass percent, mole fraction, and molality. Right, molality is lowercase m. Okay, those are 5 concentrations. Okay, and for the homework we're going to encounter next week, a big part of the homework will ask you to get familiar with the concentration term conversions. So you're going from, let's say, the molality into mass percent, or fraction or polarity. Okay, so those are the things that we need to actually encounter. So you can actually make sure that big part of the questions you can answer those things correctly. All right, cool. So these are the. I have another questions for you today. I think that's pretty much it for today. Let me see. Yeah, this is actually for the next lecture. So let's go. All right, so these are the things we're going to go through today. So we finished the in the past lectures, and then we're going to finish the remaining one today. And we're starting from talking about the solution formation. Okay, so how a solution is formed. Okay, when you throw a salt into water to form the salt aqueous solution, what really happens at the molecular level? Okay, so those are the things that we're going to talk about first. Okay, so here you see I write this equation. So delta H solution equal to delta H solute plus delta H solvent plus delta H of mixing. Okay, so what is delta H mean? Yeah, what is enthalpy? Yes, heat. Okay, heat is a form of energy. Okay, so in chemistry, there are actually two things that's very important. One so-called the thermodynamics. Okay, one called kinetics. Okay, so in nature designed the world in a very interesting way. Okay. So nature wants things to happen in a direction that you minimize your energy. Okay, and then you make things as random as possible. That's the nature. Okay, so what do I mean by that? Human get lazy, right? Lazy is a lower energy state. Okay, and if you don't have a good plan, you will eventually become a lazy person. Okay, so that's an analogy you can have in mind. So things like to go to a lower energy state is just nature. Okay, you cannot always run like you cannot always throw like 100 miles per hour for a baseball, right? You have to drive yourself like crazy to achieve that high speed. Okay, but in normal situation, okay, the things that happen to us is that things will go to a lower energy state. Okay, so delta H is actually one of the physical parameters that scientists use to describe energy. Okay, so don't get scared when I write this delta H. It's just a symbol, it means nothing, just talking about the energy. Okay, so the delta means what? Change. Okay, it means actually when this thing happens, how is the energy compared to its initial status? That's what delta means. Make sense now? Okay, so once you know what delta H of solutions, then you know let's actually calculate the solution overall property beginning and after you calculate difference to get the delta H solution. All right. So now I have three extra terms: delta H solute, delta H solvent, and delta H mixing. Right. So think about the salt. What is actually a chemical formula of salt? NaCl, sodium chloride. Right. So how does it look like? A white powder in the solid form, right? Once you throw it into water, what does it become? Do you still see white salt in the water? No, if the concentration is actually not too high, okay, it fully dissolves, right? So when you throw the NaCl solid into the water, eventually, what does it become? Why can't I see it anymore? Yes, it dissociates and becomes what? Ions, which is Na plus and Cl minus. Okay, they become ions. Okay, the reason that you can see as white powder in the solid form is because they form crystals that arrange in a very specific way, form a big chunk of species that the light cannot pass anymore. That's why it is white. When we store it into waters, okay, one thing everybody can see now is that it dissociates, means it breaks itself apart, right? So break things apart takes energy. Okay, so let's move the first term. Delta H solute means I need to break apart my solute now. So instead of breaking apart the solute, it takes energy. Scientifically, you're going to have a positive sign. Okay, because you need to give energy to make that process happen. Right? You want to break it apart, you actually give energy. So once you give energy to that specific system, in this case, sodium chloride, right? Then the sodium chloride will get energy to make this happen. Okay, therefore you have a plus sign over there. Okay, and break apart a solid typically cause pretty big energy cost. Okay, you actually spend a lot of energy to make this process happen. So we put on that the sign of your delta H solute is always positive and always large. Okay. How about your solid? It depends, right? When we form a solution, okay, of course, the things we discuss the most often is that your solvent is just water. Okay. So water is already in the liquid form. Therefore, if you want to bring them apart further than its original status, this can actually give in some energy, but the energy will be much, much smaller compared to your delta H of your solute. So this one will be also positive, but it will be small. Okay. Then we can come to the very last term, delta H of mixing. What does mixing mean? Combine. Okay, combine what with what? Yes, you can actually answer this as yourself, right? It's a combination of solvent and solute. Okay, so when we put the solvent and solute together, what do they do? They interact, right? They interact. Okay. Once they interact, they form a solution. Okay, so in the solution formation, if eventually your solvent and solute becoming a solution, meaning that this is actually a favorable process, right? Others will just don't form a solution. If eventually you see a solution to form, okay, that means this is actually a favorable process, right? That means actually the sign is actually negative, okay? But big or small, it will depend on the speed they put in. All right, so that is actually the sign that you need to know about each individual terms. Okay. So the other two things you're going to encounter a lot when you do your homework is that they're not going to say delta H solvent, delta H solute, delta H salt mixing. Instead, they're going to use this term. Lattice energy. Every time you see this keyword, lattice energies, it refers to your delta H of your solute. Okay. The other keywords you want to actually memorize is that when people are talking about delta H mixing, these are actually terms you're going to see. Hydration energy. Okay, so what does hydration mean? You interact with water. Okay, in CHEM1312, majority, probably actually more than 85 or 90% of the portion that you encounter is aqueous solution. Okay, that means actually delta H mixing will actually simplify into a term called the hydration energy. All right? So now, once you understand this, then these are the properties that you can actually measure, you can actually have feelings. And then this is actually properties that your quiz and homework will ask. Okay? So your delta H can be positive or can be negative. Okay, then we think about what it means. Okay. When you have a delta H solution is smaller than 0, meaning that it is negative, right? So if it is negative, okay, just focus on the sign and the 3 terms here. If your delta H solution is negative, okay, we have the lattice energy. We have the hydration energy. Which one should be bigger? Hydration should be bigger, right? Because your delta H is negative. And your hydration is actually the one that contributes to the negative sign. Right? So, under this case, it means the hydration process outcompetes the lattice energy of your solute. So that your delta H solution is negative. Right? So, under this case, it's going to bring your system to a lower energy state. Okay? So originally you are here, but after you create a solution, the energy goes down to here. Okay, initial, final. Okay, so you calculate delta H solution is actually final minus initial. That's how you get the negative, right? Okay. Everybody understand the energy is always going to conserve. Right? So what happened between the energy in between? What happened to all this heat? Need to go somewhere. Right? Where? Go to the environment. Right? So it's going to release those energy difference into the environment. Okay, so once you mix these things, all this energy will come out. Okay, once it comes out, like what happens? Once you actually have this salt chloride that mix with the water, right? Energy to release. What is actually the neighbor? So this is actually sodium. Surrounding is actually all water, right? And it's going to release a lot of energy once they actually hydrate, right? Then the energy will go to the neighbors, right? The neighbors inside a container is actually also water, but the water doesn't actually directly interact with your sodium plus or chloride minus, right? So once those water got heat, then what do? They boil, they increase their temperature. Okay, so those are the things that you need to know. If those are things you will be tested. Okay, so get back to here. We know you're going to release energy, right? Therefore, this process will be exothermic, right? Exo means release. Okay, I'm going to release the energy, so it's exothermic. Okay, the heat was released, right? So these are equivalent description, right? And the very last one, you can see the temperature is going to increase, right? Because your surrounding water molecule are going to get those heat and bump up the temperature of your solution. All right? So we're going to go through a few examples afterwards so you can actually get the things more clearly. Okay. So the bottom line is basically just the opposite. Right. Oh, there's actually one more thing I want to add. Okay. So here you will say your hydration energy is outweighing your lattice energy. Okay, so hydration is the delta H of mixing. Lattice energy is actually delta H of your solute. Okay, so those are the terms you'll be tested. Okay, so make sure you know all this relationship. Okay, if you can actually see the physical pictures, answering this is actually really simple. Right, but the problem is actually it's very difficult to see the physical picture just from the equation itself. Right, you see how much time you spend to actually get those pictures to you. Okay, but once you have the pictures, things actually become very easy and it will start to make a lot more sense. All right, any question for this? So if not, let's introduce another concept, then we will do some examples. Okay, the other important concept we want to actually understand today is the solubility. So when we talk about solubility, it's actually the amount of solute that can actually goes into your solvent. Okay. So there are actually two different types of question I'm going to encounter for this specific concept. So the first type of the question you're going to encounter is actually if I give you a multiple species, three species, A, B, and C. Okay, then I will ask you among the three, which two will dissolve with each other better? Okay, so the way you make the judgment for those kind of questions is the concept is actually very simple. The concept we want to use is this. Light dissolve light. Okay. Put it in a more scientific terms. Okay, so we're going to use these two terms a lot when we discuss those kind of problems. Hydrophilic and hydrophobic. Okay, so what does hydrophilic means? It's water-like, right? Hydrophobic is water is like. Okay. Translate into a chemistry version will be organic-like. Okay, so everybody have an idea about what the difference is between organic molecule and the aqueous or hydrophilic molecule? I guess not.
Organic molecules have the CH bond.
Yeah, so I will give you some hints and use this one as a guide. And try to do this. Hydrophilic molecule, typically, you want to actually have a very specific component inside your chemical formula. Okay. You see a chemical formula contains NH and OH. Very likely they are hydrophilic. Okay. How about the hydrophobic? Hydrophobic one will actually contain. If you see a equation only contains carbon, hydrogen, or halides, then they will be organic. Okay. So when I say halides, for this course, I will strongly encourage everybody to print out one periodic table and put a sign in order to doing all these questions. Okay. Because we're going to referring back to this a lot. When we say halides, it's actually this column. Column 17, column 7A. Okay, so whatever shows up on the columns, they are halide groups. Okay, so if you see a chemical compound that only have carbon, hydrogen, and whatever atoms here, they are organic. They are hydrophobic. Okay, so those are the two very simple things that you want to actually memorize. Okay, and then the other thing that you want to learn, which you already learned from your 10 11, is that the polar molecules would like to dissolve inside water. Okay, it will dissolve better than the non-polar one. Okay, so here you will actually need to know how to determine whether a molecule is polar. Okay, which is our in 10-11. Okay, so if you know how to predict which molecule will dissolve better with which, then the next thing we want to talk about is the factors that's going to affect the solubility. And here we only talk about two factors. One is temperature, one is pressure. Okay. So I guess this was you're going to see this, even if you don't come to this, from your daily experience, you know. Once the temperature increases, the solubility of solid will go up. Right? So I guess that makes sense to everybody. The things gets interesting is that if you have gas as your solid, this will be the opposite. But again, from your daily life experience, you should have that too, right? From increase of temperature, the solubility of gas is going to be less, right? When you put your Coke under the sun, after an hour, drink it again, you feel disgusting. Because there's actually no carbonates inside your Coke anymore, right? They all evaporated, meaning that the solubility becomes less. Okay, so if temperature goes higher, the solubility of the gas molecule will decrease. Okay, so let's actually the effect of temperature. Pressure. So the pressure will only be relevant if your solute is gas molecule. Okay, so we have three physical states for most of the material, right? Solid, liquid, and gas, right? Solid and liquid is very difficult to compress. Okay, meaning that they're actually very resistant to change of pressure. Gas is actually only phase. That is actually sensitive to pressure. Okay, so talking about pressure, everybody familiar with what pressure is? Not pressure in the psychology, but pressure in physics. Okay, so how is the pressure generated? Collisions, very good. Very smart. Yeah, very good. Yeah. Collision. Who collides who? So what species collide what to give you the pressure? Gas molecule collide on the container, the surface of everything. Okay, so that's how you get the pressure. Okay, so it's really the gas molecule. Okay, see, every time we talk about pressure, it's all about gas molecule. Nothing to do with your solid, nothing to do with your water, nothing to do with your liquid. Okay, it's only gas. Okay, so when we talk about the effect of pressure on the solubility, it will only be relevant for your gas molecule. Okay, so larger the gas, better the solubility, right? So how do we actually get the soda? You pump CO2 into your water, right? Everybody have the soda stream machine at home. You open this tank, right? And those tank is actually containing CO2. It was pumped into your water container. So the CO2 goes into your water. So when you drink it, it evaporates. So you have this fizzy feelings. Okay? It's all about chemistry. Okay. So larger the pressure, greater the solubility for the gas. Okay. There's actually one thing that you want to know. Is the only equation that associated with the things we just described. It's called Henry's law. Okay, so what it says is the concentration of your gas which is C, is going to equals to a Henry's constant times the pressure that you apply. Okay, so the Henry's constant is actually a characteristic properties of different type of gas. Okay, not all the gas dissolve in water at the same level. They are all slightly different. Okay, and the main thing that dictates the solubility will be how does the gas molecule interact with your water. Okay, so but for a given gas molecules, this is a constant. Okay, so higher the pressure, higher the concentration you are going to get for your gas molecule dissolved inside the water. All right. So I want to go to a few examples so we can get the things more clear. Okay, question number 6. A flask containing ammonium chloride becomes colder as water is added, and then the salt dissolves. If the magnitude of the lattice energy of NH4Cl, which is ammonium chloride. So this and that, they are the same. Okay, is it larger or smaller than the hydration energy of the ion? Okay, so when you read these questions, the first things I want you to pay attention to is that what are the keywords? What are the keywords here? Colder is one. That's good. That's another two. What other things I could emphasize when we talk about this topic? Lattice energy. That's actually another term. Okay, so we set up the stage for you for the previous 20 minutes, right? We keep repeating all these things, including the lattice energy and hydration energy, right? And then it gets colder. Okay, so that's actually the things that we actually know, right? So, but question that we're gonna ask is actually trying to know. Which one is actually bigger, right? So once you see this lattice energy, hydration energy, you know it's testing the concept that delta H solution equals to delta H solute plus delta H solver plus delta H mixing. Right? These are the questions I want to write down. These are the questions that you think of. Okay? And then you know the things that matter is actually this first term and the last term. right? And it says that the things become colder. Colder means what? Delta H is positive or negative? Positive, right? So how do I actually make sense of this? So we didn't actually talk about this specific condition previously, right? Previously, what we do is what? We talk about delta H is negative condition, right? Where the hydration outweighs your lattice energy. Then you release that energies to the neighbors, which is other water molecules. Therefore, water molecule temperature goes up, right? This is just the opposite. Because this actually temperature goes down, right? So it becomes colder, right? And it's actually, when you do this hydration, you pull the energy from the neighboring water molecule. So that overall things become colder. Does that everybody follow the things I just said? It's not. Let's go back. Let's talk about this again. So here we say the delta H negative, right? Exothermic. Okay. Heat release from the interaction go to your neighboring water molecules. Temperature increase. Right. Under this case, your delta H is negative, meaning that your delta H mixing outweighs delta H lattice, meaning that your hydration energy outweighs your lattice energy. That is actually what we described in the previous condition, right? But the question that we encounter is like, it says the temperature decrease, right? Because it says become colder. Right, colder means actually temperature is going to decrease. That means you need to actually absorb heat from your water molecule for those interacting partners. Okay, that means it is actually an endothermic reaction. It means your delta H is positive. It means your lattice energy is actually bigger. Right? So you have the correct physical pictures in mind. So when you actually encounter the informations, then you know how to respond properly. All right. So that is actually how you solve question number 6. I hope this makes sense to everybody. Okay. Any questions for this? Okay. Remember, the key is to understand everything I say in the in-person lecture. Before you walk down the door, you want to know these are the things that you must understand. Okay, because it's a lot easier for me to explain to you right here, right now. Okay, you can get answer right away. If you walk out the door, it depends. Right? So I would strongly encourage that you actually get everything straight before you leave this room. Okay, so the other type of question you're going to encounter is this. Which of the following is actually more soluble in water? Methanol or CCl2H2? Okay, so first thing first, you need to know what other things you want to actually dissolve in. It's water, right? So remember we say like dissolve like. Water is Water is what? Hydrophobic or hydrophilic? Hydrophilic. That means you want to actually find a molecule that is hydrophilic. Right? So what is actually the property of hydrophilic molecule? It must have what? I read two terms previously, right? Yes, don't make your life too complicated. That is complicated enough already. Okay. You realize that I try to actually make things as simple as possible so that I can actually memorize it. Okay, and remember the course you are taking is what? Gen Chem 2. General. simple. If you feel like you need to think very hard, take a big look, you are doing things wrong. Make sense? Yeah, so it's general chemistry. It's just lab testing you some very simple rules. But do you know the rules? Do you know the simple rules? That's the key, right? What I do is actually tell you what the simple rule is. Tell you what to memorize. So memorize it. Okay? So if you have NH, OH, hydrophilic, okay, if it's actually hydrophobic, then what you are looking for will be C, H, and halides. Okay? So if you look at this, what's this? C, Cl2, H2. Contains what? C, H, halides. Therefore, you know the second one is hydrophobic. What is hydrophilic? Then force it out. You know that cannot be your answer. Then you know the answer has to be methanol. Right? But what is methanol? Do you see that big OH? Those are things you need to look for. Once you see it, then you know how to answer these things. Simple? Yes, it should be like way, okay? So if you're not doing things this way, you will make yourself too complicated. You'll make your grade looks miserable. Okay, so don't do that. Okay, it's CHEM1312. All right, so those are the conceptual things we want to go through. Then we can actually go to the very big topic today, which is the collective property. Okay. So what these things means is that all these properties is only relevant to the number of solute particles inside your solution. It doesn't care about what kind of particle that you have. Okay? Specifically, 4 different terms, okay? Vapor pressure, boiling point, freezing point, osmotic pressure. Each term has its associated equation. Okay, but before it goes into the equations, I would strongly encourage you memorize by knowing that vapor pressure and freezing point, they are a pair. Boiling point and osmotic pressure, they are a pair. Okay, so when you have more solute particles inside your solution, you are going to have lower vapor pressure, lower freezing point. Okay, so let's say I put lower here, and then for this one, it will be higher. Okay, for your boiling point, and then for your osmotic pressure, it will be higher. Okay, so let's actually number one concept you must have. Okay, having this concept can already allow you to answer some of your homework problems. All right, so then the other very important concept for the collective property is that you must get familiar with the concept of Van Hoff coefficient. Okay, so Van Hoff coefficient, we use the symbol I here. Okay, to represent it. Okay, so the I is so-called the Van Hoff coefficient. Okay. So what do I mean by that? Okay, let's give you some examples. So let's say you have 3 different solutes you want to throw into water. Okay, let's say you have the same amount. There's always 1 m of each species. Okay, the first one is what? Methanol, right? The second one is sodium chloride. The third one is calcium chloride. Once you throw this species into water, what happens to them? They dissociate. They interact with water, right? They undergo hydration. Okay. So if you throw methanol into water, methanol is going to interact with your water, right? So what's the identity of methanol? It's going to become something else. Anyone know the answer? If you throw sugars into water, is the sugar still exist as sugar? So you say it's going to become CH3O minus plus H minus. Okay, so this is very potentially become important. Okay, so not all the OH can be dissociated like water. So this won't actually happen. Okay, so what happens inside the water? When you throw your methanol inside, it will become this. Okay, so the thin central layer is what? It's forming the hydrogen bond. Okay, but the structure of your CH3OH still intact. It doesn't really change. Okay, so we call this type of molecule. Because this is actually a term that you need to actually memorize. Non-electrolyte. Okay, so if the things you look at doesn't belong to acid, doesn't belong to base, okay, doesn't belong to salt, then they are all non-electrolyte. Okay. Many things you see, actually majority of things you see, they can dissolve inside water. It is actually non-electrolyte. Okay, for example, sugar molecules is non-electrolyte. Okay, many of the proteins that we have is non-electrolyte. Okay, so as long as the things can form a strong hydrogen bond, okay, they can be a non-electrolyte but will dissolve in water. Okay, so this is a very important concept that you must take it away from CHEM1312, because I realize many students do not realize that. Okay, so therefore you know, since you have one molecule thrown in, you dissolve one molecule. Van Hoff coefficient was simply equals to 1. Okay, and this is true for all the non-electrolyte. Okay, to become an electrolyte, you can either be acid, base, or salt. Okay. How about this? What happens when you throw the sodium chloride into water? It fully dissociates. and it becomes what? Very good. Okay, so I want to see the difference between the first example and the second. Okay. The first example tells you the molecule 3 still stay the same way it is structurally at the molecular level. Okay, it just forming the interaction with the water, so that it can dissolve inside the water. Sodium chloride is a different story. You throw in NaCl as a compound, you throw it in, then it immediately actually dissociates, becomes sodium plus and Cl minus. And sodium plus interacts with your water, Cl minus interacts with your water, and then they both dissolve. Okay, so here you throw in one more, but you get 2 particles out of it. Okay, so you know the I will equal to 2. And the way you say it is 2 is because you count the number of solute particles that you will generate once they dissolve in water. Okay, keywords, solute particles. Okay, you're going to see these keywords in your questions. So make sure you have a sense. If you see these things, solute particles, it actually including sodium plus and Cl minus. Okay, that are your solute particles. Okay. How about your CaCl2? This one will become Ca2 plus 2Cl minus. Right? So how many solute particles that you have? 3, right? Therefore, the I is going to be equal to 3. All right, so this is a very, very important concept that you must have. Okay, any questions for this? I hope everybody now has a good idea what blank hole correlation is. Okay, and you can differentiate the difference between the non-electrolyte and electrolyte means. Okay, of course, here I will give you the example of salt, right? So it's NaCl, calcium chloride. How about this? HCl, strong acid. Once you throw into water, it will fully dissociate. What's the blank hole coefficient of that? 2. Okay. You need to be very confident when you answer this type of question. Okay, so you know you can actually do your homework quickly. Okay. All right, so those are the things that you want to know. That's the second thing I want to mention. Okay, and the third thing that we're going to step into all these equations. Okay. So the 4 properties we're talking about: vapor pressure, boiling point, freezing point, osmotic pressure. They are actually properties of your solvent, not solute, solvent. Okay, so but the amount of solute particles you throw in will prevent or help related to certain things. Okay, so for the vapor pressure, the equation that you want to actually memorize is the Raoult's law. Okay, so the vapor pressure of your solution will be the mole fraction of your solvent times the vapor pressure of the pure solvent. Every time you see these little circles on the top right corner of the symbol, okay, it means either pure substance or it's actually at a standard state. Okay, so in this case, it's actually pure solvent Okay, so this is actually a vapor pressure of pure solvent. Okay, so when you store in more solute particles, the more fraction of your solvent becomes smaller, right? And then all the particles stored is going to occupy some of the area on the top. Once a solute molecule is deposited on the top, it prevents your solvent to evaporate. Once you prevent them to evaporate, they won't have a chance to hit the wall of your container. They won't produce the pressure. Okay, therefore, if you store more things actually into your solution, then its vapor pressure is going to decrease. Okay, but the way you calculate quantitative of the vapor pressure of a solution, then you go to Raoult's law. Vapor pressure of your solution equals to more fraction of your solvent times the vapor pressure of pure solvent. Okay, so this is based on the fact that the things that you store in, it is non-volatile. Okay, so every time you heard this term, non-volatile means it doesn't evaporate. Okay, so since it doesn't evaporate, then the only thing they do is just blocking your solvent molecule from evaporation. Therefore, it won't produce vapor pressure. Okay, so the more you throw in, the lower the vapor pressure will be. Okay, and then let's talk about the freezing point. Okay, so freezing point is going to get lower if you have more solute molecules. Okay, so then you have to understand what this freezing point means. Okay, so freezing is a process that your solvent molecules will come together form a nice lattice and become solid, right? Using water as an example is the process that your water become ice, right? So when the water become ice, what it means is actually all the H2O that align with another H2O in a periodic way. They're getting so close, eventually become a solid. Okay, now think about this. You have some solute molecules. Okay, they're going to get in the way, right? So if I want to actually form a solid with another water molecules, there's actually another guy here prevent me from doing that. Okay, so what should I do? The only thing I can do is actually I keep lowering down my temperature, right? So that even though I cannot immediately go to that guy, okay, maybe I hope when I lower down the temperature, maybe there was some other water molecule come nearby, then I can actually form a solid with them. Okay, so things your solute particles actually preventing your water molecule from solid from each other, right? You go to even lower temperature to make the things become a solid with a lot of defects, of course. Okay, so because of that, then if you throw in more solute molecules, you will need to actually go to an even lower freezing point to make the solvent freeze. Okay, so if you throw in more solute particles, then your vapor pressure will decrease. Then your freezing point will decrease. Okay, so the equation you want to actually memorize is this. The change of your freezing point, okay, the delta TF, okay, TF means actually the change of your freezing point, can be calculated using this very simple equation, I times Kf times your molality. Okay, so Kf again is a constant, will always be provided inside your equation. So if you know how to calculate the molality of your solution, then you can actually predict how much temperature change it will be. Okay, but see here, because it's talking about the change, right? If you want to know the final freezing point, then you know it will be your normal freezing point minus the absolute value of your delta Tm, right? Because it's going to get lower. So it will be your normal freezing point subtract that differences. Okay. So the very last two we want to talk about is the boiling point. Okay, so boiling point and then your osmotic pressure is similar things. Boiling point meaning the process that your water molecule want to go into the air. Like if you're going a lot of solute molecules, if you're ready to go to the air, they actually heat it even more, so that you can actually fully boil. Okay, so here equation wise it's the same. These two are very similar. Okay, you calculate the change of your boiling point. It's going to equal to your vector coefficient I times KdP times your molarity. Again, if you want to know your total final boiling point, it will be your normal boiling point plus your delta TB. Okay, so these are the things that you want to know. Okay, osmotic pressure, typically we use things called pi. Okay, and then if you calculate using I, vector coefficient times your molarity times R times T. One thing that you want to be very careful is that the R, which R should we use? AEN, yes. Okay, so everybody, when you do your midterms, you're going to have a table like this, right? Underneath, it will give you all the coefficients. Okay? It will include in a term called your R values. Okay, you can either 8.314 or 0.082. Okay, look into that unit. Pick the one with ATM. Okay, so here, make sure that the R you use is 0.82, 0.082, okay? The unit will be liter ATM per mole per K. Okay, so this will be the correct R to use. If you use 8.314, you will never get the correct answer. All right? So these actually are the things that I want to, sorry, I forgot one of the things here. Okay, but that's actually what you know for the osmotic pressure. Okay, yeah. Sorry, I previously forgot this, right? Talking about this non-volatile solution. And today, what you have, we're going to move back to the vapor pressure again. Okay, so previously we talked about your solute is actually non-volatile, meaning that it won't contribute to your vapor pressure. But today, the things that you throw in, they can also evaporate. Okay, then to calculate the total vapor pressure of the solution, it will be the sum of the both terms. Okay, because right now everybody can do your, so this one will be the vapor pressure of your solution will equals to mole fraction of your solute times the vapor pressure of your pure solute plus mole fraction of your solvent times pure vapor pressure of your solvent. Okay, so it's very simple, just linear relationship, nothing special. Yeah, I just realized I missed that point by the equation. Okay, so those are all the concepts that you need to have for chapter 10. Okay, next week we're going to finish all the unfinished examples that we have inside the hangout, so you can know all the calculations that you need to know. Cool. Yeah, so we're stopping here. Thanks.